Alright, so we've been looking at a special type of motion called uniform circular motion. We have a particle that's moving along a circle. It could be moving clockwise or it could be moving anti-clockwise. But what circular motion means is that it moves with a constant radius about some point, right? We chose the axis such that the origin is at the center of this motion. And using those polar unit vectors that we talked about, namely r hat and theta hat, you're able to write the position vector very simply, the position vector in time, as r into r hat t. If you differentiate this once, you get the velocity vector. And here we have uniform circular motion, where we have the particle moving along the circle with constant speed. Another way to think about it is that this angle theta, this changes at a constant rate, so that this omega equal to d theta by dt, which is the rate of change of theta, that's a constant. And we are able to write this vt as r omega theta hat t. So notice that at each point on the trajectory, the velocity points tangentially to the circular trajectory, right? Which is in the direction of theta hat. Now our constant omega, which is d theta by dt, a positive rate of change of theta means that theta is increasing with time, which corresponds to anti-clockwise motion. And a negative d theta by dt corresponds to a clockwise motion because theta is decreasing with time. Okay, so we have the magnitude of this vector. Because theta hat is a unit vector, we have the magnitude v equal to r omega, so the linear speed, which is a constant because this is uniform circular motion, the particles moving along this circular track at constant speed. So v is a constant. That's related to the rate of change of theta, also known as the angular velocity, right? So the linear velocity is simply related to the angular velocity by this formula v equal to r omega. Now, this particle is not experiencing any change in linear speed, but that does not mean that it's not accelerating, because the direction of its motion is changing constantly. So this particle is indeed accelerating, and if we differentiate vt with respect to time one more time, we get at equal to minus r omega square r hat t. And the reason why it's called centripetal acceleration is that, as you can see, this acceleration vector at each point on the motion points in the opposite direction of r hat t, which it points radially inwards, or it points towards the center. And the magnitude of this acceleration vector is given by r omega square, which is a constant. This is a constant magnitude. You can furthermore talk about two important quantities in uniform circular motion, which are the time period t, which is the time taken to cover the circular track once, and you also have this f, frequency, which is the number of times the particle finishes this trajectory per unit time, say per second in SI units. So that's as far as uniform circular motion is concerned. Obviously this is a special case, right? So what about the general case in circular motion? You now have a particle that's moving along a circular trajectory with the center at some point. So let's take the center at the origin again. In the general case, what will happen is that the particle can speed up or slow down as it goes along this circle. But if it's circular motion, the radius is not going to change, right? So r is still going to remain constant, but this time omega t, which is d theta by dt, the rate at which this angle changes, that no longer needs to be a constant, right? Because it can speed up or it can slow down, it can change direction, and so on. Correspondingly, the linear velocity, which is simply given by r omega t, is going to also change. So let's look at that. Now we again have rt equals to r times r hat t. Again, because it's circular motion, this r is indeed going to remain a constant, okay? But let's differentiate that. Again, if you differentiate this, you once again get r d theta by dt theta hat. The thing we do here is that we have to remember that r hat changes with time, because at each point on the trajectory you will have a different r hat, right? So that those different r hats at different times, you have to differentiate that, and you'll get the differentiation of r hat t is going to give you theta hat t. You could carry out the differentiation in Cartesian coordinates if you so choose. We've written those here. But anyway, this time d theta by dt is not going to be constant. And notice that if you take magnitude here, you're still going to get v equal to r omega t. That is, the angular velocity, which is omega t, is related to the linear speed via this formula, but this time, because omega t is no longer constant, the linear speed is no longer constant. So the example you can think about is turning on a fan. Initially the tip of the fan is at 0 speed, right? But after you turn it on, it slowly speeds up, and it speeds up, so the linear speed keeps increasing, which is related to the increase in angular speed, right? By multiplying it with the radius of the fan, you get, just by multiplying the radius of the fan with the angular velocity at each time, you get the linear speed of the tip of the fan at that time. Anyway, let's differentiate vt one more time to get acceleration by definition, right? At is dv by dt. But then to differentiate this, or to differentiate this expression, you need to use the Leibniz rule, right? The Leibniz rule says that if you have a product, then to differentiate it, you keep one part of the product constant, differentiate the other part, and well, this is something you must have used a lot of times. So you differentiate this product and you get the following expression. Finally, you get at equal to r d square theta by dt square, which just means differentiating theta twice, right? Times theta hat minus r d theta by dt whole square r hat. To make some sense of this, let's define this quantity d square theta by dt square as alpha t. And what this is well, because d theta by dt is omega t, this is the differentiation of omega, right? But what was omega? Because omega was angular velocity, right? Omega was angular velocity, so it makes sense to call this quantity angular acceleration, okay? So this quantity is angular acceleration. We shall see why that is, but at this point you plug this definition into this formula, you get at equals to r alpha theta hat minus r omega square r hat, which is something that makes a lot of geometric sense, as we shall see immediately. In the general case, therefore, we get that this at, this is no longer simply pointing towards a radial direction, right? Remember, in uniform circular motion we had this centripetal acceleration, it was always pointing radially inwards. At this point, in the general case, what we find is that there is a component that points radially inwards, and it looks like r omega square, and that this component does indeed change with time. Remember that in the general case omega changes with time, so we do still have this radial component, which is, we call this the radial acceleration or the centripetal acceleration. You always need centripetal acceleration to have circular motion, right? So let's write that down. Always need this for circular motion. But you also have an extra piece, which is a theta equal to r d squared theta by dt square, which we've defined that to be alpha, right? D squared theta by dt square, so it's r alpha or r d omega by dt. And this, because it points towards the theta hat direction at each times, we call that the tangential acceleration or the angular acceleration. So, like, if you think about some instant in time in circular motion, you have this quantity a r hat. So that's the centripetal piece, which, as you see, it still points, radially inwards because it's got that minus sign right there. So that you have this, right? You have a piece in this direction. You have, a component of this vector, right? You have a component of this vector pointing radially inwards, but you also have a component that points, either tangentially in this direction, or it could point in this direction, depending on whether this R alpha is a positive or a negative number, right? So let's look at all this in detail now. First, let's think back to the special case. Okay, the special case was uniform circular motion. What was that? In the special case, the d theta by dt, which is omega, was a constant. In which case, alpha, or d squared theta by dt square, is d omega by dt. That's 0, right? So hence we have, for uniform circular motion, we simply get back the expression that we had always, which was at equal to minus r omega square r hat, right? That's the expression we derived particularly for uniform circular motion. So at this point, we are starting to make sense of what this angular acceleration quantity is. Namely, zero angular acceleration corresponds to the fact that the speed r omega remains constant in uniform circular motion, right? If the speed r omega remains constant, then omega must not be changing with time, so the differentiation of that, the angular acceleration, is 0. What about non-zero angular acceleration? What does that do? So again, in the general case of circular motion, you have at some time t, you have the particle at some point on this circular trajectory, right? And the radius vector is given by r hat t. And then vt is given by r omega theta hat t. So notice that even if this particle, while going along this circular track, even if it's speeding up or slowing down, the velocity at some instant in time points tangentially to the circular trajectory, right? It could point in, say, this direction. If omega t is positive, it could point in the same direction as theta hat t, meaning that it's undergoing an anti-clockwise motion at that instant in time, or it could point in the opposite direction of theta hat t. But the point is that if you truly have circular motion, then there should be no radial component of vt. Vt at some instant in time only points parallel to theta hat t, which one should expect because it should be tangential to the circular trajectory. Now let's look at the acceleration. It turns out that in the general case, at a given instant in time, the acceleration has a component in both the r hat direction, which is given by minus r omega square, so that's the centripetal component, right? You have a centripetal component given by minus r omega square t r hat, and you also have a tangential component, a component that's tangential to the circle at that point. So that could point, as we said, in the same direction as theta hat t or in the opposite direction. Let's say alpha is positive. Alpha could of course be changing with time, by the way, but let's say for now it's at this instant in time it's a positive quantity, in which case we would have another vector that points in the same direction as theta hat t. Let's call this, and this would be r alpha theta hat t. Now that we have a component in this direction, of the acceleration, of course the total acceleration would be the vector sum of this and of this, right? Which is exactly what this expression here, alpha t. The expression for alpha t just means that the total acceleration in the general case is a vector sum of these two vectors. So now that we've written up the components of the acceleration vector, it's very clear what this r alpha does, right? All it does, because you notice that at each instant in time, because velocity points, in the same direction as theta hat. It's parallel to theta hat. It could point in the same direction or opposite direction. So what R alpha does is that it's able to change the velocity. It's able to change this linear speed, which again is to be expected because this, as you see, alpha is d squared theta by dt square, or d omega by dt. It changes the linear velocity. It changes the angular velocity, right? It's the rate of change. We can write that down. Is the rate of change of angular velocity. But what does the change of angular velocity mean? It means that if you have this theta, if you have the rate at which this theta is changing, if that's not constant, it's changing, then either this particle must be speeding up or slowing down. So everything makes sense. What this R alpha does is that it changes the linear speed at which this particle is covering this trajectory. So hopefully at this point the roles of both R alpha and R omega square are clear, which is, R alpha is alpha is the angular acceleration, R alpha is gives you the tangential component of acceleration at some instant in time, and R omega square is the centripetal one that's causing the particle to stay in a circular trajectory. Of course, also understand that both omega square t, that could be a function of time, right? The centripetal acceleration could be changing with time. In fact, it should be changing with time if alpha is not equal to 0, because alpha is just d omega by dt. If alpha is a non-zero thing, then this centripetal acceleration must be changing with time, right? So let's write down a short summary of everything that's important. So the summary is that you have, in the general case, the acceleration vector at some instant in time in circular motion looks like the sum of a centripetal part minus r omega square r hat and a tangential part r alpha theta hat. So centripetal acceleration is ar equal to minus r omega square, and you must remember that omega is d theta by dt and alpha is d square theta by dt square. So actually these two things are related to each other. Let me explain in a little bit. So acceleration, the centripetal acceleration is ar, or it's also called the radial component of acceleration, is minus r omega square. This is the thing that causes the body to undergo circular motion. If you don't have centripetal acceleration, you don't have circular motion, plain and simple. And the angular acceleration, this is what causes, if you have a circular motion in which the body is speeding up or slowing down as it covers this circle, then you must have angular acceleration, and this angular acceleration is what causes the speed to change in circular motion. If this alpha is 0, or if the rate of change of omega, that is d omega by dt, is 0, then of course you have the special case of uniform circular motion. You simply have centripetal acceleration whose magnitude is not changing with time, and you have a theta, the tangential acceleration, is 0. That was the special case of circular motion. Alright, so that's it for now. In the next lecture we shall work out a problem in which there is angular acceleration. We shall try to look at these quantities in the context of some real life problems. Thank you.